So this is a question from GATE 2016 from Chemical Engineering, question number 47. The liquid phase reversible reaction A reversibly giving B is carried out in an isothermal CSTR operating under steady state conditions. The inlet stream does not contain B and the concentration of A in the inlet stream is 10 mole per liter. The concentration of A at the reactor exit for residence times 1 second and 5 seconds are 8 mole per liter and 5 mole per liter respectively. Assume the forward and backward reactions are elementary following first order rate law. Also assume that the system has constant molar density. The rate constant of the forward reaction rate in second inverse rounded off to the third decimal place is dash. So this is a question from design of ideal reactors from Chemical Reaction Engineering, and the reference NPTEL series can be found in Module 1, Lecture 17, Design of Mixed Flow Reactors, Chemical Reaction Engineering 1, Homogeneous Reactors by Professor K. Krishnaiah, Department of Chemical Engineering, IIT Madras. So here in this question, a reactor or reaction A reversibly giving B is carried out in two different cases. So case 1, the residence time tau is 1 second, and case 2, the residence time tau is 5 seconds. So in case 1, the final concentration of Ca is given as 8 mole per liter, and in the case 2, for a residence time of 5 seconds, the concentration of Ca is given as 5 mole per liter. Right. So residence time here basically means the space time. So we can directly solve this question by using the design equation for CSTR. So for CSTR, we have the design equation tau is equal to Ca0 minus Ca by minus Ra. So this is the design equation for CSTR. What we'll do here is, we'll do this design equation for both the cases. So case 1, they have given that the space time or the residence time is 1 second and the final outlet concentration is 8 mole per liter. So in the design equation, tau is equal to 0 minus Ca by minus Ra. Here 1 is equal to Ca0. So the initial concentration they have given us 10. And here in case 1, the final concentration is 8. So 10 minus 8 by minus Ra. Okay. Now let us find an expression for Ra. So the reaction here is a reversible reaction, A reversibly giving B, and the reaction rate can be expressed as, let's take the forward reaction rate constant as K1 and the backward reaction rate constant as K2. So we can write this reaction rate expression as minus Ra is equal to K1 Ca minus K2 Cb. Okay. Now we know that Ca is 8 mole per liter here. So from this we can find Cb. Cb will be 2 mole per liter. Okay. So how we found out this is, we can find the conversion Xa as 80% from the values of Ca and Ca0. So that means 20% of, sorry, my bad. So from Ca, basically we can find the conversion. So Ca is equal to Ca0 into 1 minus Xa. So that means 8 is equal to 10 into 1 minus Xa, and Xa is basically 20%. And Cb will be Ca0 into Xa, and that will be 10 into 0.2, and that is 2 mole per liter. So we found out Ca as well as Cb. Now we just substitute it in the design equation. So design equation is 1 is equal to 10 minus 8 by K1 Ca, which is basically into 8, minus K2 into Cb, which is basically 2. So 1 is equal to 10 minus 8, that is 2 by 8 K1 minus 2 K2. Or we can rearrange this as 8 K1 minus 2 K2 is equal to 2, or 4 K1 minus K2 is equal to 1. So let's take this as our equation 1. Now case 2, we repeat the same thing. Here the residence time is 5 seconds. The final concentration Ca is 5 mole per second, and from this we can find the conversion Xa as 50% or 0.5, and using this we can find Cb as Ca0 into Xa, and that is also 5 mole per liter. So again we write the design equation. Tau is equal to Ca0 minus Ca by minus Ra. That means tau, which is 5, is equal to Ca0, that is 10, minus the Ca, final Ca here is 5, by minus Ra, which is K1 Ca minus K2 Cb. We just found out the values for Cb as well. So just substitute it here. 5 is equal to 10 minus 5 by K1 into Ca. Ca is 5, so 5 K1 minus Cb is also 5, so 5 K2. So that is 5 by 5 K1 minus 5 K2. Now if we can cancel out all these 5's here, and this will be 1 by K1 minus K2, which is equal to 5. Now rearrange this. 5 K1 minus 5 K2 is equal to 1. This will be our equation 2. So now basically we have two equations. The first equation being 4K1 minus K2 is equal to 1, and the second equation being 5K1 minus 5K2 is equal to 1. All we have to do is solve these two equations with two variables and find the value for K1. So to solve this, what we'll do is, this is equation 1, this is equation 2. So we multiply equation 1 by 5 and subtract this with equation 2. So what we'll get is 15 K1, and the K2s will get cancelled while we do this mathematical solving, and 15 K1 will be equal to 4, or K1 is equal to 4 by 15, which is the forward reaction rate constant, and in terms of decimals K1 will be equal to 0.267. So this is our forward reaction rate constant. And the forward reaction rate constant here is K1, which is 0.267.